10.2 is a section that has too many topics, so I'm trying to break it down into two. It starts with test for convergence. And we start with a theorem. If a series is convergent, C for convergent, D for divergent, then the limit as n approaches infinity of a sub n being the general term of the sequence, that must equal 0. Now, what if the limit equals 0? That doesn't tell you anything. The contrapositive of this, so this is A implies B. Something like, if it rains, there must be clouds. If it rains, then there must be clouds. Well, if it doesn't rain, that doesn't mean there are no clouds. And what if this happens? If there are clouds, that doesn't mean it's going to rain. But the contrapositive would be, if A implies B, not B implies not A. If this is an authentic if-then statement, that is, if there are no clouds, it cannot rain. Logic. So we take this definition, which really we don't use much, and we use the reverse. We say, if this doesn't happen, then this cannot happen. If the limit as n approaches infinity does not equal to 0, if that doesn't happen, then this does not converge. Does not converge means it diverges. D for diverge and C for converge. So this is how we show a series does not converge or diverge. That's the easiest way out if it's possible, if the limit doesn't equal 0. And here they say show that the series are divergent. A couple of examples. We're going to go back to section 1.4. That's when you found the horizontal asymptote, and they talk about how to do this. You take the limit as n approaches infinity of this general term of the sequence. And how do we deal with rationals? From section 1.4, we divide by the highest power term of the denominator. So we have 3 over 1 plus 5 over n plus 1 over n squared. Now, any value over n, as n increases, any number over n will go to 0. That would be 3 over 1 plus 0 plus 0. This limit will be 3, which doesn't equal 0. So we took the sequence part and we showed that that limit doesn't equal 0. Therefore, the conclusion is that this series does not converge, and if it doesn't converge means diverge. And this test, if you ever use it, you have to quote it, test for divergence. That's our conclusion, based on reversing the above theorem. So we're really using this. We're just using this theorem to derive the test for divergence. If I look at the second example I have, well, the same deal. I'll take the limit as n approaches infinity of 3n over 2n plus 1. You divide by the highest power term of the denominator. In this case, that is 2n. So I'm looking at the limit as n approaches infinity. The denominator is 1 over 2n, and this is 3 halves to the n. That is the limit as n approaches infinity of 1 plus, this is a 0. That is the limit as n approaches infinity of 3 over 2 to the n. And 3 over 2 to the n is an exponential function. It's growing because the base is bigger than 1. We covered that already. Remember, we did exponentials and logs. We did the graphs. As n approaches infinity, this will approach infinity, which does not equal to 0. Therefore, the series diverge by test for divergence. Okay, now this section is a bit lengthy, so I'm breaking this into two lessons. One part is going to be mushed together with 10.1 and the other will be the remaining of 10.2. We have the integral test. Given a series, an infinite series of a sub n, if this a sub n happen to be positive, continuous, and decreasing, we let a sub n equal f sub n. Then, this series will converge if this integral exists as a finite number, section 4.7, and this original series will diverge if this integral does not exist as a finite sum number, if you get infinity or negative infinity. For section 4.7, we dealt with these integrals, so it's not something new. You did that in your past life. So let's start with the first problem. And here, they're really doing this straightforward, meaning they're telling you use the integral test, so you should mention that this is positive, continuous, and decreasing. If they're saying use the integral test, that means that's the case. What you have to do, you have to integrate from 1 to infinity, 1 over, so f of x is 1 over x squared dx. If this integral exists as a finite number, this series converge. If it doesn't, it diverge. Well, we know what this is. This would be the integral. So this is how I play around infinity in there. I ignore it until the last step. This is x to the negative 2 dx. That would be x to the negative 1 divided by negative 1. Basically, it is negative 1 over x evaluated from 1. And we use a variable t and let the limit of t approaches infinity. That's section 4.7. You could review that if you wish. And you look at this. This will be the limit as t approaches infinity of negative 1 over, throw the t in, minus throw the 1 in. As t approaches infinity, that will be a 0. So this limit will be a positive 1, which is a finite number. We say, therefore, the series n equal 1 to infinity of 1 over n squared converge by the integral test. Next problem on the list. Again, if they're saying use the integral test, you should know that this is positive, continuous, and decreasing. So I would take the integral from 1 to infinity of 1 over square root of x dx. I know that this is x to the negative 1/2 dx. That would be x to the 1/2, 2 over 1, evaluated from 1 to t, and taking the limit as t approaches infinity. That is the limit as t approaches infinity of twice square root of t minus the square root of 1 is 1. As t approaches infinity, this will approach infinity, and infinity plus any number is infinity. So this is not a finite number. Our conclusion, the series n equal 1 to infinity of 1 over radical n diverge by the integral test. Now, this gives us a conclusion, sort of. If I'm looking at the series of 1 over n raised to a power, by the integral, we know if that power is 3 or 4 or 5, this is going to converge. And if that power is 1 or less, it's going to diverge. And that's what brings us to the p-series. Oh, look at that. That's shifted. The p-series is a quick way for you to figure out whether a series converge or diverge. That is, you glance at a series. If it is n raised to a number, if the number is bigger than 1, we know the series converge. And if the number is less than 1 or equal to 1, the series diverge. Very simple. An example, if I let p equal 1, I'm looking at the series n equal 1 to infinity of 1 over n. Well, this is positive, continuous decreasing. The integral from 1 to infinity of 1 over x dx, well, we know what that is. That is natural log of absolute value of x, evaluated from 1 to t, taking the limit as t approaches infinity. So that is the limit as t approaches infinity of natural log of t minus natural log of 1. That's a 0, but that's infinity. And infinity minus 0 is infinity. Therefore, we know it diverges by the integral test. So instead of doing all of that work, if you recognize that this power, in this case, is a 1, if it's 1 or less, the series diverge. And you could quote by the p-series, and you don't have to do the integral test. Here, they're saying to use the integral test, so we are going to use it, but in other sections, the p-series will be very useful. How about here? Well, the same deal. You would say that's positive, continuous, and decreasing. So I'm looking at the integral from 1 to infinity of x squared over x cubed plus 3 dx. So here, I would let u equal x cubed plus 3. du is 3x squared dx. And by now, hopefully we're comfortable with this. There's my u. And there is my du. So a u is right there. And a du with a 1/3. And we know this is, we know this will be 1/3 natural log of absolute value of u, 1/3 natural log, and we know u is x cubed plus 3, evaluated from 1 to t, taking the limit as t approaches infinity. That is the limit as t approaches infinity of 1/3. Throw the t in. Natural log of t cubed plus 3 minus natural log of 1 plus 3 is 4. But the limit as t approaches infinity, this will be infinity. So I'll be left with 1/3 into infinity minus natural log of 4, which is infinity. That's not a finite number. Therefore, the series n equal 1 to infinity of n squared over n cubed plus 3 diverge by the integral test. So again, there are 3 different tests, and they're kind of lengthy. I want to break them up into 2 sections instead of 1. 1 more to go, and we're done. The last problem we're looking at is, let's go for E. Let's skip D. D is the same as what we just did. There we go. So this is positive, continuous, and decreasing. If I integrate from 0 to infinity, 1 over x squared plus 4 dx, I know what this is. This is 1 over 2 inverse tangent of x over 2, evaluated from 0 to t, and taking the limit as t approaches infinity, limit as t approaches infinity of 1/2, inverse tangent of t over 2 minus inverse tangent of 0 over 2. Well, that's a 0. The limit as t approaches infinity, we are responsible for only one graph of inverse. As far as we're concerned, the graph of inverse tangent looks like this. It maxes at pi over 2 and minimizes at pi over 2. Since t is approaching infinity, that will approach pi over 2. So I'm left with 1/2 times pi over 2 minus 0, which is pi over 4. That is a finite number. Therefore, the series n equals 0 to infinity of 1 over n squared plus 4 converge by the integral test. So I am going to stop here. There are 2 more tests left in this section. I will finish that up with the next lesson.